Alright, we are now getting ready to start a new section here in Chapter 3, Section 5 on exponential and logarithmic equations and some of their applications. Now, an exponential equation is an equation in which the variable is in the exponents. That's kind of an easy definition to remember. And to solve an exponential equation, we have to approach it one of two ways. We have to either be able to use the equivalence property of exponential expressions, which I'm going to explain in a minute, or we have to use logarithms. Now, the equivalence property of exponential expression says if b, x, and y are real numbers with b greater than 0, not equal to 1, and then b to the x is equal to b to the y implies that x equals y. If we can get the bases to match, then we can set the exponents equal to one another. That's an important property. I'm going to use it in both of these examples. By the way, I did it again. I forgot to circle this one. This is one off the review. So is that one over there to my right. First things first, we'll look at this a little bit simpler one because it only has one side that's written with a variable expression. And this is 4 to the 2x plus 3. Now I look at 64, and 64 I think of as 4 times 4 times 4. So I'm going to rewrite this as 4 to the 2x plus 3 is equal to 4 to the third power. And if the bases are the same, I can set the exponents equal to one another, and I have a very simple equation, subtract 3, divide by 2, that I can solve. And I can go back and plug it in and check to make sure my answer is okay. So that one was kind of nice because 64 is a power of 4. Now over here, 16 is not a power of 8, 8 is not a power of 16. It's not going to be quite as convenient as this last example, but I know that 8 and 16 are both powers of 2. 8 is 2 times 2 times 2, or 2 to the third, and 16 is 2 times 2 times 2 times 2, 2 to the fourth. So I'm going to replace the 8 with 2 to the third power, and that's raised to 3x minus 4, and I'm going to replace the 16 with 2 to the fourth power, and that's to the x minus 9th power. Because I have a power raised to a power using my properties of exponents, I can write this as 2, multiply the exponents, that would be 9x minus 12, and 2 to the 4x minus 36, power to a power, multiply the exponents by distributing. My bases match, I can set the exponents equal to one another. I just didn't leave myself very much space here. So I'm going to kind of streamline this a little bit. I have the variable on both sides. I'm going to subtract 4x from both sides. I'm going to add 12 to both sides. And I'm going to divide both sides by 5. And I get x is negative 24/5. And that's my answer. Alright? Now, if I can't match the bases like I was able to do here and here, then I've written out the steps that you would want to use to solve this type of exponential equation. Alright, isolate the exponential expression first on one side of the equation. Now in my first example, the exponential expression is already on one side of the equation isolated, so that's good. Then I'm going to take the logarithm using the same base logarithm on both sides of the equation. You would use a common log or you would use a natural log, most likely because if they ask for an approximation, that way we can use the calculator. You're going to use your powers property of logarithms to, quote, bring down, unquote, the exponent so we can get at it, and then we're going to solve what's left. So in this example here, if I take the natural log of both sides, and then I use my powers property of logarithms to bring my exponent out in front. And then I can solve for x by dividing both sides by the natural log of 5. And I get x equals the natural log of 83 divided by the natural log of 5. Now remember, this is a division. You do not try to subtract the 83 and the 5. That's not the quotient property. It's the natural log, or any kind of log of a quotient, not quotient of natural logs. That's as far as that one goes, unless they ask for you to solve it to, I don't know, however many places they want you to, decimal places, and then you grab your calculator and you can do that. I'm going to stop here. This guy over here, I have to do step 1 in this example because I'm going to have to get this guy isolated. So I'm going to add it to both sides. I'm going to add 1.73 to the x power to both sides. See, now it looks a lot like this problem. I've got the variable over here on the right. I'm going to take the natural log of both sides. I'm going to use that powers property, bring it out in front. And then I'm going to divide both sides to get the variable x all by itself by, and I'm going to flip-flop sides here, by the natural log of 1.73. So I'd get the natural log of 200 all over the natural log of 1.73. And again, that would be probably a good enough answer that you could leave it in that form. If they ask for a decimal place, then you just go ahead and get your calculator out and then you can approximate that. Now I have a couple more equations I'm kind of interested in showing, but I'm out of space. So if you can bear with me, give me just a moment. I'm going to erase this and see if I can do a couple more equations. Lots of equations in this chapter, and I have a couple more equations that involve the variable and the exponent. Okay, and again, I'll say that the directions say solve. We'll use this as part A right here. Alright, so I'm going to solve this one. I need to isolate the variable. I should say the exponential expression that involves the variable. So I'm going to divide both sides by 700. And I'm going to flip-flop sides. I'm going to write 700 e to the negative 0.2k divided by 700 is equal to 100 divided by 700. And you say, well, it looks a little bit like the last example. Well, a little bit. I am dividing, but the key that's different is the fact that if I do take the natural log, and I would not take a common log here, I would take the natural log because this is base e. If I take the natural log of both sides, the natural log of e to a power is just that power. Oops. So if I divide both sides by negative 0.2, which is the same thing as negative 1/5, so it kind of be like multiplying by both sides by the reciprocal of negative 1/5, which is negative 5. Negative 5 times negative 0.2, which is negative 1/5, is positive 1. Now, if you left your answer like that, that's not the world's worst answer. But I will tell you this. A lot of times, students have trouble matching answers that involve logarithms because there's different forms. For example, in this particular problem, I could rewrite this as k equals negative 5, the natural log of 7 to the negative 1, because 1/7 is 7 to the negative 1. Use my powers property and rewrite this as positive 5, the natural log of 7. So you have this, and you look in the back of the book and you have this. And you think you've done something wrong. No, it's just a matter of rewriting. In fact, they might not even leave it like that. They may use their powers property again and write this as the natural log of 7 to the 5th power, or they could get their calculator out and approximate that all the same. So be on the lookout there when you get answers that involve logarithms like that. It might be rewritten. And here's another example. I'm going to work out 6 to the x plus 4 power, call this part B, is equal to 8 to the 2x minus 5 power. Hope I left myself enough space. Maybe I can squeeze it in here. I'm going to see that I cannot match the bases. Wasn't able to do back there as well, or over there as well. But what I'm going to do here is I'm going to take the natural log, and you can use a common log. I just like the natural log because I only have to write 2 letters instead of 3. And then I'm going to use my powers property, but I have to be extra careful here because my exponent is a binomial. This side as well. Bring this out in front, the natural log of 8. Now to get at the x's, I've got to isolate them, so I'm going to have to get rid of parentheses by distributing. And I have x, the natural log of 6, plus 4, the natural log of 6, is equal to 2x, the natural log of 8, distributing here, minus 5 the natural log of 8. Now this term's got the variable and this term has the variable. They're on different sides. I need to have them on one side. I think actually normally I bring stuff to the left so the variable's on the left, but excuse me, I'm going to go ahead and bring the variable to the right side this time instead. So I am going to subtract x natural log of 6 from both sides, and I'm going to add 5 natural log of 8 to both sides. See if I can squeeze that in. This is going to get kind of confusing here. X natural log of 6 plus 4 natural log of 6. I'm going to subtract x natural log of 6, and I'm going to add 5 natural log of 8. So that's the left side equals. The right side is all this again. Fortunately, this is going to simplify a little bit. And then I am subtracting x natural log of 6, and I am adding 5 natural log of 8. Just got it there. All right, these are going to cancel. I'm going to have 4 natural log of 6 plus 5 natural log of 8 is equal to, these are going to cancel, 2x the natural log of 8 minus x the natural log of 6. By the way, I did it again. This is one that you would see on the review. All right, so now I'm going to get my variable. It's in both terms. I'm going to factor it out. I have 4 natural log of 6 plus 5 natural log of 8 is equal to x times the quantity 2 natural log of 8 minus the natural log of 6. I factored out the x, GCF, and then I'm going to divide by this. I'll flip-flop the sides one more time. I get x equals 4, the natural log of 6, plus 5, the natural log of 8, all over 2, the natural log of 8, minus the natural log of 6. Oh, good Lord, there's all sorts of things they could do here. They could, because you have natural logs here and such, they could bring that power up there. They could rewrite this a couple different ways. Most likely they'll ask for an exact answer, and if you're left like this wouldn't be all that bad. If they ask for a decimal, if I'm not mistaken, this is approximately 7.42, I think it's 0.1 to 4 decimal places, to the nearest 4th decimal place. The nearest, what, 10,000th. All right. Now there are other types of equations. I just don't have the space to do them here, so we're going to pick that back up in the next video.